I will pretend that this is all fine. So, so teaching is a hard object to model from a to understand from a computation point of view, partly because of concerns that some of you raised. Essentially, teaching can be seen as conveying information from one point to another, so you get these information theoretic bounds, but that's pretty much all we can do because who knows what the true function is for a cat recognizer, for example. So then let's move to the third topic, most relevant one for the class, which is the teacher is neither helpful nor hurtful. All it does is it randomly picks examples, applies the function to them, and gives it to the learner. And so it gives maybe these about 10 or 8 or 10 examples, 8 examples, right? So this is protocol 3, which is supervised learning. Now, this is pretty much the only thing that the teacher does. The teacher labels these examples and walks away and does not bother. There's no more interaction with the learner. As a result, what happens now is the learner has to do what it can with this data. So one easy algorithm that would work with this kind of data is first assuming again that we know that we are okay. If you throw out all the negative examples, you're left with these 4 highlighted rows. And now look for those variables that are present in every positive example. So this variable x100 is present in every positive example. That means, in fact, let's look at another. Let's look at those variables which are absent in any positive example. So x99 is absent here. What that means is this example is labeled positive despite the fact that x99 is 0, right? Which means x99 couldn't possibly be in the conjunction. You can do that. You can essentially, every 0 in a positive example eliminates variables. So this example eliminates x99 is eliminated. This one eliminates x98 and so on. And what you do is you look at the rest of the variables that survive and you make a conjunction out of them. That's a reasonable thing to do. And what you could get is you could get a conjunction that says x100 has survived all the positive examples because it's present in all of them. x2 is in all of them, and also x1 is in all of them. So it learns a hypothesis that by eliminating all the variables that are absent in anything, any of the positive examples, it could learn a hypothesis that is x1, x2, x3, x4, x5, and x100. Whenever the reason x100 survives is because it just so happened that in this particular randomly chosen set of examples, just by accident, whenever the output's 1, x1 is also present. So there's no way that the learner can eliminate x1. Yeah.
So you said that you can make something like this with active learning. So my question is if you have the initial labeled set,
yes,
and you eliminated a certain amount of variables,
then you can ask each one.
Then you can ask each one on the smaller set.
Yes.
And they can be.
That's right. That's right. And this is the answer to your earlier question. Yes. So the thing to note is all we have is this data set. I'll get to you in a minute. All we have is this data set, and we did not learn the true function. The true function did not contain x1. The learned function contains x1. We have only learned an approximation of the true concept. And the question we have to ask ourselves is H good enough? How many mistakes can H make in the future? We have a question.
Shouldn't this be a batch algorithm because we have all the data at once?
Sure, it can be a batch algorithm.
So why is it under the topic of online learning?
Oh, this is this is under the topic of online learning, mostly because this is the first analysis of learning algorithms that we are encountering. And I want to make the point that even before we start analyzing learning algorithms, we need to first agree on how the learner and the teacher can interact with each other. Different ways in which the learner and the teacher interact changes the complexity, the learning complexity of the concept. So this is the most version that we will look at, and under this we will look at multiple different protocols. Yeah.
Now, could we, since we're looking just for positive examples, could we also look at the negative examples and kind of get a cross section of both of them?
I will leave that question as an exercise because I want you to think about whether the negative examples would give you anything more than what we've already got.
Well, you can argue that negative examples will tell you that you are right because you don't know if you don't know the function.
It'll only give you. I'm going to make a proposition that negative examples will only help you verify, but will not give you new information.
Exactly.
But think about that and let's move on. So the point is, we have a situation where we've learned a function, and through no fault of ours, through no noise in the data, the function that we learned is not the right function. Notice that this is a case where we did not learn the right function, not because of any noise or any adversary. This is the only data we have. And now the question is, how do we know we are good with this, or how good is this? And there are two broad styles of thinking that we can pursue. The first one that I'll mention, but that will be the next topic we'll get to, is the probabilistic intuition. The idea is that the large data set that we had only 8 examples, but let's pretend it was a large data set. The large data set that we had, which was sampled randomly, did not have had X1 always on whenever the label was on. Maybe X1 is always going to be on just by accident. Maybe the distribution of the data, that the distribution that generates the examples is such that it is skewed towards X1 being on whenever the label is on. Whenever X2 is true, X1 is true, and so maybe that's how life is. Maybe because our data set was so large, in the future, the possibility that X1 will be off when the example is true is going to be rare. In fact, it's going to be so rare that it's not going to bother us too much, and we won't make too many mistakes in the future. This style of thinking, if you formalize this, gives us what's called the PAC framework for learning. PAC stands for probably approximately correct learning. And we'll get there after we finish online learning. Now we're going to look at another protocol, and this is the answer to your question, which is maybe what we'll do is, instead of thinking of this as a batch of examples, we're going to encounter one example at a time. And we will update our hypothesis every time we see an example. The elimination algorithm can be, that we saw just now, can be easily extended that way. If you see a positive example, we have a current hypothesis, you remove all the variables that are 0. That's the update. And then we can define good in terms of how many examples do we have to encounter before we can guarantee that there will be no more mistakes in the future. Okay? Now that's a heavy statement. How could you possibly tell that there will be no more mistakes in the future despite having never seen the future? How do you know that you've finished learning, so to speak? Yeah.
Wouldn't it just have to be that you have seen every single possibility?
Oh yeah, sure. But that's a trivial large upper bound that we are hoping to beat. That's an exponentially large number. And when I formalize it, I'm going to argue that we want our mistake-driven, we are going to define mistake-bound learning to be the kind of to be a learning algorithm that can do better than that. Can do anything better than that. We don't want to explore the exponential space of algorithms in something. So that's where we're going to go now. Did you have a question? Okay. We're going to look at online learning, and the point of this whole setup so far was to illustrate that how the learner and the teacher or how the learner and the function interact with each other determines how many examples we need before we can define that we can state conclusively that we've learned the function, or we can hope that we've learned the best possible function. And in order for us to even decide that, we need to first decide on how the teacher and the learner interact with each other. The version of the interaction that we are going to explore quite in detail in this class would be this sort of a disinterested teacher that I described, where the teacher just labels a random collection of examples and moves on. This is supervised learning. And this is the most dominant kind of learning setting that we have out there, because any data set that you can think of is all you have, right? You sometimes have the luxury of going out and asking for more labels. You never have the luxury of probing into the minds of people and asking them to reveal to you what a cat looks like in their brains. So the only case that you have is the case where you have a data set and you have to do something with it. You have to do the best possible thing you can. So specifically, we're going to look at a framework for learning called online learning, but I want to step back and look at the big picture. In our previous lecture, we looked at linear models. We're going to look at, we are asking the question of how do we know that a learning algorithm is good enough? There are different ways of answering that question. One way of answering that question is online learning. If you intersect online learning with linear models, you'll get algorithms like perceptron, which we will cover in class and which you will implement in your homework, and Winnow, which we sadly will not cover in class, but this is the Winnow style algorithm keeps getting reinvented every decade, and I think they're due for one this decade. And at that time, it will come back to the class. Another style of thinking, answering the question, is PAC, or empirical risk minimization. And when PAC meets linear models, you get something like support vector machines or boosting. Different named algorithms that just are, their intellectual lineage comes from those things. Another answer for how good a learning algorithm, which is in the ... there, is the Bayesian criterion, where we want to talk about a probability over hypotheses, and we define goodness as if I learned the most probable one. And if you apply the Bayesian criterion to linear models, you get things like logistic regression, naive Bayes, and such algorithms. Essentially, most of this class is going to be this interaction between how good is a learning algorithm and different hypothesis spaces, and by intersecting them, you get different named algorithms. So we are currently inside this one, and next in the next week's lecture we'll go to this one here, and together your homework 2 will be basically all of that. Okay, so let's go into online learning. In particular, online learning is a broad family of things. We will not have time to cover it in great detail. So we look at a specific version of that called mistake-driven learning or mistake-bound learning. And this, as I said, gives you different kinds of learning algorithms, which actually eventually will, after we look at perceptron, I'll try to bring back a perspective around gradient descent, which is a more general version of this. As we talk about this, I want you to keep a few things in mind. Everything here is predicated on the assumption that we know what a good representation is. We know what good features are. We won't talk about that here, but it's important. Another question is complexity of learning. Complexity of learning could take two forms, actually three forms. One is, of course, the time complexity. How long does learning take? How much work, how much computation needs to be done for learning? Another one is space. How much memory needs to be in place? How much memory does the learning algorithm need to have? Does it need to store an entire data set? Can it not store everything? The third kind of complexity, which is not typically seen in an algorithms and data structures class, but is more, it's homegrown in the machine learning universe, is called sample complexity. How many examples are needed before we know that learning is done? So all three kinds of complexity are interesting. And then I want you to keep this thought about features in mind. How do we know we have the right features? Maybe we don't. So we have to make assumptions. So let's talk about the mistake bound model first. Just to give an example of an application where this might be useful, is suppose we have 1,000,000 features. I think that's 1,000,000. Suppose they have 1,000,000 features. We don't know what are the right features, so we've gone crazy and invented 1,000,000 of them, hoping that the learning algorithm will discover the right function. Now, suppose in this scenario, the true function is actually does not need all those 1,000,000 features, and it's just these 5 features that we looked at. So the function is suppose very, very sparse. It depends on at most k features, but we don't know which of those k are relevant. One example of that is spelling correction. Here's a sentence with a typo. Can someone spot the typo? It's a subtle typo that I can imagine myself making. This should have 2 S's. It's still a valid sentence. The word is still valid. So you have desserts or deserts, and you know that this is wrong because of this word that's present there. And so the presence of that word changes the probability that this word should be a single S or a double S. Right? So there is a certain feature. Oh, see, I underlined it also. So the problem is that word is just one word. We don't know which of these words corresponds to which S, and maybe we want a sort of a first cut would be having Boolean features that say the word sweetness present in the context is the word cat present in the context. You go through the entire dictionary, and for each one, the feature is it present or not? This might seem like kind of a silly way of doing things, but trust me, this is not very far from how things are done. And now the learning algorithm has to figure out that for desserts with 2 S's, words like sweetness are relevant, and that could be maybe X100 could be that feature. And that's a very small set of relevant words compared to the entire dictionary. So we need to now find a learning algorithm whose complexity, for whom the difficulty of learning does not depend on the ambient dimensionality, but on the number of relevant features. In this case, it's just 5. Can we develop algorithms that can have that property? One question that comes up that's immediately relevant is maybe that depends on our hypothesis space assumption. Maybe if you knew that a certain hypothesis space is the one that needs to be explored, life gets easier. With this example in mind, let's look at mistake-bound algorithms. I mean, I'm going to just formally define what mistake-bound algorithms are. As always, we have instances. Our instance space is the set capital X or script X, and it's an n-dimensional space. There are n features. The target function is f, which takes an instance and maps it to a single label, true or false. F is inside the concept class. For now, we'll assume that the learner knows what the concept class is. So the learner knows the concept class, it knows the hypothesis space. So the size of the concept class, we'll see why later, but assume for now that the size of the concept class, the number of functions that are in C, is dependent on the dimensionality. As the dimensionality increases, the number of functions increases. The learning protocol that we will explore is one of online learning. The learner is given an example that is randomly chosen. When it sees an example X, it has a current hypothesis that it's using, it has in mind. It uses its current hypothesis to make a prediction. The prediction is h of x. After it makes the prediction, the true label is revealed. F of x is given to the learner, and now the learner knows whether it has made a mistake or not, and if it made a mistake, it can choose to make a correction. And this is one round of learning. So learning essentially proceeds in rounds. This is just one round. And remember, I talked about memory and all that, the space complexity. Here, the space complexity is negligible because it keeps nothing in memory. It does not get to keep every example it's seen so far it has only enough memory to store that one example that's currently being presented, the hypothesis, and maybe a few bits for these labels. That's all the memory it has. Now, we need to also define what it means for a mistake, for the learner to have made a mistake. At any point in this round, the learner is said to make a mistake if the prediction of its current hypothesis is different from the ground truth. That's a fairly reasonable definition of a mistake. If the learner makes a prediction and then finds out later on, after it makes a prediction, that its prediction was wrong. That is, f of x is not the same as h of x. Okay? Now, given this, let's define a few terms. One quantity of interest could be, say we have a sequence of examples S, and there is the learner is currently running an algorithm A. Learner is running an algorithm A on the sequence of examples S, and let's say the true function is f. For this sequence of examples, this particular algorithm may make a mistake here and not make a mistake there, and so on. We can count how many mistakes are being made on this sequence, right? This is something that we can actually count if you knew the algorithm and the sequence. Let's call that A of f and s. So it's a property of the algorithm, the true function, and the sequence of examples. So far, so good. So I see two heads nodding. I'm going to assume that, yes.
So can you say that just one more time?
Yeah, thank you. Just general thing is if you're confused about something, chances are 20 other people are. So that it's always good to kind of ask me to say something once more. So there would be, so let's say that we have a learning algorithm. Okay, so let's call it a learning algorithm. There's a box A that's currently executing something that looks like this. And what it does with the feedback is what defines the learning algorithm. Okay, this is essentially this box here. It sees a sequence, there's an assembly line of examples that go in. Example 1 goes in, each circle here is a labeled example. The learning algorithm gets an example, it makes a prediction, and if its prediction is wrong, it can choose to update its hypothesis, and then there's a counter, maybe this one made a mistake. Then maybe at this point, this was a mistake, this was not a mistake, so this was wrong, this was wrong. Right? For this particular sequence, maybe it made a mistake on something and not on some others. Here, MA could be 2. There are 2 mistakes on this particular sequence, for this particular algorithm, for this particular target function. If it was a different target function or a different sequence or a different learning algorithm, maybe it would be doing, the count would be different. Yes.
So is all it doing is keeping track of the number of things that got wrong and not the specific examples that it got wrong?
Yes. All it does is keep track of the number of mistakes. Of course, it's that, by the way, the algorithm is not keeping track of the number of mistakes, we are. All the algorithm is doing is what's in the box there. It sees an example, makes a prediction, receives feedback, and makes a correction. What we are doing is we are observing the algorithm, because remember, the goal that we have is to ask whether this particular algorithm is good or bad. So we, as people who are analyzing this algorithm, are keeping track of the mistakes. I saw your hand first, and then I'll come to you. Yeah.
In this sequence, so each circle, so this is representation of a set of features.
A set of each circle is an example.
So example is basically
Feature
feature values.
Yeah. Yes. You, then you, and yes.
I just want to clarify, algorithm A is learning target function.
Yes. A is trying to learn target function F. Yes.
So you said that it updates itself when it knows that it's wrong.
Yes.
So wouldn't it improve over time, the number of mistakes should go down?
That's the hope. That's the hope.
So, like, how would you quantify how good it was if it's supposed to be getting better over time? Initially, it would say that more were wrong, and then as it got better, it would
We want to keep track of the aggregate, and your answer is literally the next thing that I'll talk about. But Yes.
So when you say it updates itself or corrects itself, is that just picking another function in the concept class?
Yeah, yeah, essentially making edits, any edits. That's the luxury that we are giving to the algorithm designer. We are going to allow the algorithm designer to perform whatever correction may be necessary. And that's what differentiates one algorithm from another. But effectively what it does is it picks a different hypothesis. There were other hands, I thought. Okay, if there are none, let's move on. So this is the property, MA of Fs is a property of a particular algorithm for a particular sequence for one particular function, right? Now, how do we know what of these things do we get to control? As the algorithm designer, I can choose algorithm A or algorithm B. As an algorithm designer, I really don't get to control what the sequence is because the examples are randomly chosen. So I can't really talk about learnability with respect to a particular sequence because I don't get to control how my learner will explore the world. Not only that, the algorithm designer can't control what the true function is. The only hope we have is that the true function is some function inside the concept class. The only assumption that we make. So in some sense, this property here is, while easy to compute, not particularly useful because it does not tell us, it depends on things that we don't control. It depends on, in particular, F and S. The algorithm cannot control which sequence of examples because remember, this is not active learning. The algorithm cannot control which sequence of examples it retrieves. It cannot control which function is the true function because if it knew the true function, then why bother? Yeah.
In control of it.
We are hoping to make that as small as possible. So in some sense, the only things that we know when we are designing the algorithm, we are assuming we know, is what the algorithm is and what the concept class is. So we want some property of these two things. Yeah?
Just a vague idea that in time series problem, so we basically might have a relation between this example. So they're not basically randomly chosen.
Oh, we are assuming they are randomly chosen. We will, for the rest of the class, we'll assume examples are random.
Okay. And this-
Independent, actually.
I'm just comparing this with time series example.
Sure.
So I'm just saying that will that learn faster compared to this, given everything is constant for both of them?
Or slower. If there are dependencies are adversarial. That changes
Okay,
things.
so it has to learn the features among the.
It changes things in ways that are much harder to formalize.
Okay, intra-learning and inter-learning also.
I don't know what intra and inter are,
Intra is
but
basically among the.
sure, but the general thing is if you start thinking about dependencies between the sequence of examples, that makes things so much harder. Yes.
Why is this not active learning? Because the protocol seems like it's a form of active learning.
The reason it's not active learning is because the learner does not get to ask questions. The learner has to live with whatever example shows up.
But is not making that the prediction, is that not?
No, active learning is where the learning actively chooses which examples should be labeled. The active part of it is in deciding X, which this learner does not have access, control of. I saw some hand here. If not, let's move on. Let's define another thing. The thing that what I mentioned was the learner does not get to control what F is, the learner does not get to control what S is, and in an adversarial case, both of these could be the worst possible thing. So we could ask for a concept class. Imagine for a concept class, see, we have, by the way, is this font visible at the back? Is this too small? The subscripts and all that? Good. Okay. So we have a concept class C. Let's say that we have the worst possible function. By worst, I mean by some measure, the most difficult possible function to learn. And imagine for that difficult function, there is an adversary who's picking a sequence of examples. Okay? So we have an adversary who wants to force this particular learning algorithm. Maybe the adversary knows about how the internals of this algorithm works. And the adversary wants to force this learning algorithm to make the maximum possible number of mistakes it can. So it picks the most difficult function and picks the most difficult sequence of examples, and we can ask how many mistakes will this algorithm make on this adversarially chosen function and sequence of examples. Right? It's the same quantity, except now it's the worst function and the worst sequence of examples, and the algorithm has to figure out the true function. We can ask how many mistakes will the algorithm make. Questions? Yes.
So when you say that it chooses the worst,
Uh-huh.
you're somehow quantifying how many.
In terms of number of mistakes.
How would you know what the worst? Can you construct what the worst function is and give it to the algorithm?
Let's assume an adversary of infinite computational capabilities. An adversary that is omniscient, that knows everything, whatever that word is. Right? And it knows that. Let's pretend that we assume an adversary that is infinitely powerful. The only restriction that the adversary has is that it has to explore only this concept class. It can only choose functions from within this concept class. That's the only constraint on the adversary. So now, inside this rather bleak looking setting, we're going to define that the algorithm A is called a mistake bound algorithm if even in the worst possible case, in terms of the function and the sequence, the number of mistakes is only polynomial in the dimensionality. Even in this worst possible case, the number of mistakes made by the learning algorithm for the worst possible functions for the worst possible sequence of examples is not exponential. Meaning, even in this case, the learning algorithm does not need to see the entire truth table and can actually stop making mistakes, guaranteed to stop making mistakes, without seeing the full exponential set of examples. This may seem rather difficult, right? The only thing we get to control is the concept class. Let's just by the way, this is not even the most general setting. This is a very restricted setting. There are more general settings for online learning, which include other metrics for success. A popular one in the literature involves something called regret, which the adversary chooses the learning algorithm chooses a set of actions. Actions are essentially labels that it predicts, so that it minimizes regret in hindsight. Regret is slightly more tricky, but not for this class. But if you're interested, I can point you to references. So going back to the mistake bound algorithm, a mistake bound algorithm is one that stops making mistakes, where the number of mistakes it can make in the worst for the worst possible concept for the worst possible sequence. The number of mistakes is only polynomial in the dimensionality. This is a property of an algorithm and the concept class. We can now ask for a new concept class that you encounter, like the one you will encounter in your homework. Does there exist a mistake bound algorithm? Maybe there doesn't exist any mistake bound algorithm for a concept class. So a concept class is said to be learnable under this particular model of learning if there exists a mistake bound algorithm. Maybe we don't know the algorithm, but maybe I can prove by some rather clever arguments that there exists some algorithm, maybe I don't know what it is, but there exists an algorithm that no matter what function from that concept class is chosen, no matter what sequence of examples are used, the algorithm will be able to learn the function in terms of stopping, it will not make any more mistakes after making only a polynomial number of them. If such an algorithm exists, we call the concept class a mistake bound. So the first statement is a property of an algorithm and a concept class. The second one is a property of the concept class. Yes.
How do we find that the function is burst? We haven't learned anything.
We don't get to decide that. I'm essentially when I say the function is the worst, that is essentially theory speak for we don't get to control it. So we have to be prepared for whatever the worst may be. It's just an adversarial argument. Other questions? Yes.
I'm having trouble seeing how we're gonna have an exponential amount of mistakes.
Imagine general Boolean functions. Remember that truth table that I had in the beginning of the class, where I showed you 7 examples and asked you to guess a function. Now, what I will do is then after you guess a function, and let's say I am an all-knowing adversary, what I will do then is knowing that function, knowing what your current mental state is, I will construct an example where f and h disagree, and I will reveal that next. That will be my next example in the sequence. And you are forced to make a mistake because you have to correct the function. Then after that, you have a new function. Again, I will reveal one more row. I will essentially have to reveal every possible row in the truth table. My hand-waving proof now was essentially a proof of the statement that general Boolean functions are not learnable under the mistake-bound model. We will see a much easier version of this proof in a bit. Not today, but we'll see one. But general Boolean functions are not learnable under this model. Because every time a certain row is revealed, every time imagine I'm the adversary and you are the one who's learning the function. If I know that you have a certain function in mind, I will pick an example where your function is going to make a mistake. And because the concept class is an arbitrary Boolean function, I always can find such a function. Because I can always take your example and negate. I can always find such an example. I can always take your function and force it to see what the label is on all examples and see where it disagrees with my function. There must be at least one such thing because my function is not the same as yours. So this might be, if you've never seen this kind of a definition before, this might be a bit disturbing. But I want you to keep in mind that this is just a definition. And I'll make the same statement a few more times in multiple places in the class. At this point, all I have done is defined a property of algorithms and concept classes. Maybe this is a vacuous definition. Maybe there is no concept class that is learnable under the mistake-bound model. That would be a shame because that kind of kills the rest of the lecture. But maybe that's possible. All I have done so far is just define something. I can define anything I want, and it could be a useless definition because it could define an empty set. Yeah?
Since you defined it as property of concept class, could you please tell the definition of a concept class again? It seems to me.
A concept class is a set of functions that that the oracle gets to use to choose the hypothesis, the true concept. Imagine that the oracle is also another all-powerful agent, but it has to pick a function from within some set of functions.
And that's a finite set.
That's a final. It doesn't have to be. We will look at infinite set also. It's a set of functions from which the concept is chosen. And let's assume that for now, for the sake of discussion, let's assume that the learner knows what that is. Just like the monotone conjunction example.
Learner knows the set.
Yes, the learner knows C. Let's assume that. Let's make the life of the learner a little bit easier. Here's the question.
What's the difference between hypothesis class and concept?
So this is something that probably is worth clarifying. The question was, what's the difference between a hypothesis class and a concept class? A concept class is a set of functions that the oracle can choose the hypothesis class. Let me start again. It's easier to draw this with Venn diagrams. This a set that calls capital T. This is the concept class, and the oracle can choose the true function from within this. This is a function f is inside this. The oracle can choose the true function from inside this, and we are essentially restricting the oracle to only these set of functions. A hypothesis class need not be the same as this. A hypothesis class, H, is a set of functions that the learning algorithm explores in order to discover F. We never know the true concept class. I don't know what class of functions nature chooses to define cats. All I can control is the hypothesis class. But for a good part of this class, semester, we will assume that the learner knows what the true concept class is, because that is in some sense the best case scenario. Over the course of the semester, in theory, the theory part of it, we will drop that assumption. And we'll start assuming that the learner does not know what the hypothesis, the concept class is. The learner has to make an assumption and live with the possibility, as in this picture here, that the true function does not even lie within the space of functions it explores. But for now, we are living with the happy situation that the learner maybe even knows what the concept class is. Maybe the learner knows that this is a concept class and that's equal to the hypothesis class. And it explores the entire concept class. And we can ask, what's the best you can do in this really favorable scenario? Yeah.
So you're saying that if the learner knows what the concept class is, that it becomes part of the hypothesis space?
It becomes the hypothesis. It becomes the hypothesis space.
Because it knows what it's trying to explore.
Yes, yes, yes.
So would it be accurate to say C is the set of functions that truly identify cats, and H is the set of functions that we are trying to find to identify cats?
We are trying to explore.
To explore.
Yes.
And hopefully they're the same, but we don't really know that.
We hope they are the same, and in practice, I would say it's never the same. I mean, how could you possibly even hope that they might be the same? The only reason we hope they are the same is because it makes the math a bit easier, so we make that other. Yeah.
So if your training data has every possible example for a problem that you're trying to classify or predict, right? Then C will always be a subset of A in that case.
What was the first part of your thing? I mean, I thought I followed you till the end.
If your training data was basically all the examples you could ever get for a particular problem. So your hypothesis space is really, your true function has to lie within that hypothesis space. So in that case.
Not necessarily.
Not necessarily.
Not necessarily. If I understand the question correctly, if your data set is every possible example that can possibly ever exist in this instance space, it still is only a statement about the instance space and not about the hypothesis space. If your classifier is a big table with all those examples, then C equals H, because you found the function. Okay, we should stop. We are at 10:30, and sadly we didn't get to the part where I'll convince you that there are some mistakes about algorithms. Let's see that.